So, but basically, here's our landscape. On computing stack, we are running our services on public cloud. And on top of that, we use Puppet, Terraform, and we have our homegrown deployment system, which is called Teletron. That little brown guy is called Teletron. And we also have Kubernetes today. And at the very top, we have stateless, stateful services, and storage. And programming language-wise, we have Java, Python, C++, and we also have Golang, Node.js. And believe it or not, we have several services written in Elixir. And our RPC protocol, we start with RESTful and Apache Swift, and most of our services were written in Apache Swift. And these days, gRPC is gaining popularity in the company. So also, we had heavy investments already exist today. From a security side, we have certificate management, we have a secrets management, we have a policy system, and from observability side, we use ELB, we use ELK, and we use OpenTSDB, and we also have our homegrown dashboard called dashboard. And identity, we also have identity management system. So with that, someday when we need to meet some requirement called GDPR. And in order to meet that requirement, we need to implement MTLS. And if you look at this mixture, when we do MTLS, we need to implement we need to do the change to every programming language on every the platform and for every security infrastructure. So it's a nightmare for us. And we had to use something else, which is called service mesh. And when we do our service mesh, we had some objectives keep in mind. The first one, we want unification and consistency. So for unification, we want to unify the platforms. No matter it's our service run on a VM, or run on Teletron, or run on Kubernetes, we want the same configuration, same change to cover all the platforms. And no matter it's in whatever language, we want to get the same observability and same configuration. And we make the same configuration change. We want same behavior. And the next objective is we have different services. Different services have different requirements. Some services want to roll out fast. Some services want to roll slow. And when something, unfortunately, like this happens, they want to roll back easily. And our third objective is secure. When a service talks to another service, it should be secured. It should be TLS protected. On the other hand, we also care about service mesh security itself. No matter it's a user or the CI/CD pipeline talk to the control plane, these need to be authenticated, authorized, and audited. So when the control plane talk to the data plane, this channel should also be secure. They should be protected by MTLS. And when data plane talk to a service, it should go through only loop back. The fourth objective is responsibility segregation. So still, service A talk to service B. And in service mesh world, you throw a sidecar to each of them. Then you connect the sidecars and let them talk to each other. That looks very simple and straightforward. And you just connect them. However, in the real world, especially like in a company like us, you're running thousands of level services, and things are not that simple. Why? So there are multiple players in this world, in this service mesh world. First, infrastructure. You have infrastructures taking care of your traffic. You usually have the developer experience team in infrastructure taking care of your service framework. You also have infrastructure team taking care of a service mesh foundation. And you also have a security team. Security team they take care of secrets, authentication, authorization, and auditing. And at the last, you have service owners. They control the routing, the retry policy, maybe circuit breaking, and the rate limiting, things like that. Basically, the service itself, the service behavior. So this is a model we designed for our services. So still, service A talk to service B. In this case, service A is called downstream. Service B is called upstream. Instead of treating each service as a monolithic, we slice them into 3 pieces. We have inbound, service itself, and outbound. And then we place each player into this diagram. So for infrastructure, they define the known service port. Like in this case, 8443 is the known HTTPS port. And for security, they define the security side, like what TLS version we should use, which root CA should be used, and where is the chain certificate. And for service owner, of course, he owns the service logic itself. Beyond that, they probably own the routing. When the request come into the inbound, where the request should be routed to. And also, this is the most important part. So a service owner owns the configuration of its downstream. In this case, the owner of service B controls the rate limiting of its downstream. So all the configurations are stored in somewhere called service catalog. And when our service control compose the configuration for a data plane, these ground truths are pulled in from service catalog, put together, and then generate the configuration for sidecars. And then, if you look at the outbound of the service itself, the service owner barely owns something of outbound. There are probably like some outbound. I will talk to service A, service B, service C, but there's nothing else. It's probably like some ATP options, but barely a thing. With all the objectives, here is our path to our service mesh. So start with our journey. So we had our use cases around 2 years ago. We use Envoy at our edge side. So we use Envoy to replace our infrastructures at edge. And we started with Envoy plus some configurations files serving XDS. And there is a small wrapper we call the Discover Helper, runs on host, watching some files and provide EDS. And shortly after that, we started using Envoy to implement some security solutions, like TLS, like policy evaluation. And we use policy evaluation to do, we have a wrapper around OPA to do policy evaluation, which serves the purpose of authorization. And then we use the Envoy to solve a cross-platform connectivity solution. So when we run Jupyter Hub on Kubernetes, Kubernetes runs on a single security group, which is not secure to talk to MySQL. So we use TLS, we use Envoy to serve TLS on Kubernetes to do authentication and authorization to MySQL. And then we, as we using Envoy to solve more and more problems, we realized that those config files are not suitable for this large usage. So we started building our own centralized control plane. And before that, we evaluated some popular on-market service mesh solutions, and we found more or less missing pieces. So that's why we started building our homegrown centralized control plane. And till today, we finished meshify most of our critical HTTP services. And we are in the middle of meshifying our Thrift services. And we are making good progress on that side. So our control plane is called a tower. Why tower? Because tower control planes. So it's built in Golang, and we use the Go control plane to deliver XDS v2 at the last mile. And we use Zookeeper as our storage, and we use it for messaging. So here's how it works. At the center, this is the tower, and it's on each host, or you call it a node on Kubernetes. We have a daemon set, or a daemon. It's called a beacon. So tower broadcasts the configurations and endpoints, basically XDS resources, unanimously to beacon, to every host. And on every host, we have our data plane, which is Envoy, and beacon serves XDS on each host to Envoy. So with that, I would like to let Zhimeng to tell us a little bit more about the control plane internals.
Thanks, Fuyuan. Hi, my name is Zhimeng. So I will talk about how do we design and implement the tower control plane in Pinterest. So based on previous material, we already see that in Pinterest, there's a lot of different platform we use, different language used, and different size of clusters. So when we design our control plan, there's something we want to focus. So we firstly want to make as an extendable resource distribution system, because it will not only serving our XDS resources, it also used to serve our homegrown internal configurations. Also, we want to make it very high scalable and available, because we are not talking about hundreds of machines. We are talking about maybe tens of thousands of machines. And also, we want to make it very high availability. We don't want a single point failure happens causing all the machines down. And also, a very important feature for our case is that we want to make it independent from platform. That's actually one reason that we're using our homegrown control plane, because we're using Kubernetes, we're using VM, we're using Tetron. We have several different platforms to serving the service. And also, because we have the tower and the beacon running on user host, that means we don't want the agent to take too much resource on the host, because different hosts are really using different resources. Some hosts are very sensitive to CPU, and some hosts are very sensitive to memory. So basically, we try to achieve the final performance that is the E2E latency for resource distribution, always less than 2 seconds for any endpoint change. And also, we make one tower can serve about 8,000 clients with that 16 core and 32 gigabytes VM. And also, we do stress tests every week to make sure we don't break things when we do any changes. So this is the architecture of the design. The one important thing is for the service registration and discovery, especially for the endpoints updates, because that will be changed very frequently and in very large scale. So we designed that we store the information in Zookeeper, and in each host we have a sidecar called ZK register that the service will register the endpoint information to the Zookeeper. And in Tower, we watch all the endpoint information from Zookeeper and take any changes and convert it into the EDS resource and send it to beacons. And the beacon will serve that EDS to the local host for the Envoy. So in the local host, the service can talk to Envoy locally and get all the updates from other service for the endpoints. And another thing in control plan is the configuration deployment. Besides the endpoint discovery, we also need user to control the traffic, and that we provide the Tower UI, which let user can configure like the read limits, upstream and downstream configurations, and then submit the class configuration to the Tower API, which also store the configuration into Zookeeper again. Then the Tower still watch all the cluster configs from Zookeeper and convert them into XDS results like the CDS, LDS, and RDS resources, and still broadcast to all the beacons. So in the service host, the service still talk to Envoy, and Envoy always get the latest XDS results from beacon to control any routing or CDS or LDS configurations. So that's for the configuration deployment. To achieve all the scalability, availability, and performance requirements, so this is the internal design of the component. We want to make it as fast as possible. So for the Tower design, it's basically we designed it as a stateless service, because that way we can make it easily scalable and easily recover from any failures. It won't easily causing any single failure point. And we're also using some producer-consumer model in the Tower so that it can easily be extendable to other resource type and with very little code changes. And we're using an actor-based resource store inside the Tower. That way it can have very high concurrency handling, and also very important, maintain a strict order of all the resource updates. That is important because finally we want to implement the delta-based resource distribution rather than always sending the whole resource every time. That's very important for the scalability and performance. So also under a layer, we're using gRPC streaming of the delta changes so that they can just easily sending delta to all the beacons. And for the beacons, you can see it actually using the same resource store as the Towers. That's actually the design that we make the beacon also stateless. It's always mirror the data from the Tower, so that what data in Tower, you can see the same data in beacon. That makes it very simple and very robust. And in the beacon, we also using the same producer consumer, and we actually have two different input for the beacon. One is always the update from Tower. Another is the update from the main, which only used in the restart. That's actually the local disk snapshot used. In the beacon, we're using subscription model to do different outputs for different services. We output the XDS resource to Envoy. We also output the local disk snapshot, which will be used when beacon restart. They can easily recover from local cache and then sync the latest data from Tower again. That increases the availability. If the Tower is down, beacon still can serve in the Envoy. And we also rewrite our own XDS cache based on the Go control plan, because the simple snapshot cache in Go control plan is not very efficient. In our side, we need to handle the delta more efficiently. Also, we need to handle different clusters in the same beacon, not only one cluster. So we write our own XDS cache. Yeah, so that's how do we implement and design our architecture and Tower beacon components.
Okay, thanks, Zhimeng. So after we finish this service mesh control plane, so it's come down to how our service owner use the service mesh. So it's about the workflow, and for different users, we have different workflow. And but there is one principle. When the configuration gets uploaded to control plane, by default, it's not activated. It's not used. You just add a version to that cluster configuration. And in order to use it, you need to activate. So we have two types of workflow. One is called cadence rolling out. One called agile approach. So for services like very critical, like API, like web app, like some storage, they go this cadence rolling out. We have a Git repo. So when they make changes, these service owners make changes and create a diff, get approved, then checked in. Once that diff is landed, we have a Jenkins job which upload the configurations to Tower. And from there, a Spinnaker pipeline kicks in, pick that up, and start pushing it through a predefined pipeline, just like deploy binaries. So for agile approaches, for example, some service owners, they actually do machine learning training on Kubernetes, and they want to shift their traffic very rapidly. And for this case, we have a command line tool, which is called pcloud. They can use pcloud to make config change, upload to Tower, deploy at any time they want. And here's our user interfaces. We have a control center, which is a web UI. So the user can go there to see their configurations and look up the activity history. And as well, they could diff versions either for troubleshooting or do some validation before actually activating a version of configurations. And we also have this Spinnaker pipeline, which do they configurations auto rolling out. And finally, this is our CLI tool that our users can use to do the agile approach to deploy their service configs. And after all the services, all the changes, one reality in a company like us, the reality is you don't always create new services. Most of the important services are already there. So, a key to the success of a service mesh, especially for us, is migration. How do you drive a migration? So, first, we acknowledge the fact that people naturally have a concern about changes. And with service mesh, we are fundamentally changing the way of service talking to each other. And for a big change like this, people naturally would concern. But so the way that we address concern is to help people to build their confidence. So we start with at the planning phase. We put migration as the top priority. We look at the service discovery. How do we migrate from our daemon set, the current daemon, to the new services mesh service discovery? And how we do service registration? How migrate our existing security infrastructure to the new service mesh? And next thing is collaboration. So within Pinterest, the teams driving service mesh work is there are mainly 4 teams: cloud management platform, service mesh, service framework team, security team, and the traffic team. But in order to get a successful rolling out, we actually need to involve more people. We involve all the key stakeholders. We started with some tech talk to let people understand what is the service mesh, how can they help us, and that's very important first step because people need to get familiar with the concepts before they can accept it. And then we will do some prototyping. We use service mesh to solve some MTLS challenge, and that gave people confidence. And then we did a very formal design review, and involve all the key stakeholders. And it was a big design review. We talk about the details so that people can express their concern, what is the most important to them, so that we can put all that into our design. And lastly, we had a production readiness review. When we did that production readiness review, it was very strict process, and people that certainly gave people confidence. And finally, when we roll out, finally this is the rolling out. So we start small. We roll out to several small services. When we roll out to some of the services, we start only one host. Then we go to next host. And then we basically do the exponential rolling out. And we also ask those key service owners to tierize their services. So they probably have 10 clusters. We ask them to tier to 3, we'll separate that to 3 tiers, so that we're rolling out to the lowest tier, then gradually moving to next tier. So we did find some bugs between the tiers, and we fixed them fast. And yeah, that's basically all the contents we want to talk about. And we understand that we only have 30 minutes, and there are a lot of details you probably want to talk. And we will be here during this whole conference. And if you want to hang out or talk about the details, you can either connect us on LinkedIn or catch up later. Thank you.